What's up, everybody? It's Miss Brothers. Just wanted to take you through just some information about how to successfully complete this ionic and covalent compounds practice. This is the two-sided document. One side where you are essentially taking a formula. You're telling me is that formula ionic or covalent. You're telling me the name of the compound, and you're telling me whether it's polar or nonpolar. On the other side, you're doing something similar, except you're taking the name of a compound. You're telling me is it ionic or covalent. You're doing its formula, and again, you're telling me if it's polar or nonpolar. Now, to be clear, you guys, before you start this activity, there are several things that you're going to need in order to be successful. Okay. To make it easier for you, you're going to need these notes that say ionic nomenclature. This is a 3-page set of notes. The first page talks about how to name ionic compounds if you're doing simple binary compounds. The second page is if you're using transition metals, and the third page is if you are using polyatomic ions. So you're going to want this set of notes. You're going to want this little document that says common polyatomic ions. I have a paper copy of this for you today. You can also find this in slide 30 of the daily slides, the Unit 6 daily slides. This gives you a list of common polyatomic ions, so just know that that is available to you as well. You should also have this set of notes that says stuff that you should know about chemical bonds. Again, you guys, this gives you some basic information, what distinguishes ionic bonds from covalent bonds. You should have that. The second page is important because it talks specifically about electronegativities. You're especially going to want this section right here that talks about the different electronegativity ranges. So if you want to determine whether a compound is polar or nonpolar, you have to calculate its electronegativity range. If that electronegativity range is less than, equal to, or less than 0.4, then we would say it's nonpolar. If your electronegativity range falls in between 1.67 and 0.4, then we say it is a polar covalent bond. The second half of that is just a quick reminder of different electronegativities. Remember, the least electronegative element is francium, and the most electronegative is fluorine. Now, one of the things that this tells you, this gives you some information about what electronegativity is. Electronegativity is the strength an atom has to attract a bonding pair of electrons. So what that means, as far as what's on this little table here, is that, actually bring this over a little bit, sorry guys. Thanks. It means that things on this side of the table are really, these things really will attract electrons. These things down here will give electrons away. So the most electronegative things on the planet are things like fluorine and oxygen. Okay. The other thing that you want the last page of these notes. The last page of these notes is your periodic table of electronegativities. And so these numbers that you see here, things like oxygen at 3.44 and fluorine at 3.98, that's how you're going to calculate your electronegativity ranges. And that's what this is about. That's why that's important. So we use this to give us our electronegativities, and then we use this to determine whether a compound is polar based on the difference between electronegativities. Okay. And then finally, the thing that you're going to need is you are going to need the periodic table of ions. This table of ions is important because it tells you what the charges of various elements are. Now, one of the things I want you to understand is when we are talking about things being metals, just to be clear, everything in column 1 is what we call a simple metal, meaning its charge never changes. The overall charge of every element in this column is at the top. So everything in this first column is +1, which means it's going to give away 1 electron. Everything that's in this column is also a metal. Okay? And everything in this column is going to have a charge of +2, meaning it's going to give away 2 valence electrons. Everything over here in this is column 13. Everything in here is also a metal. And again, you have to look a little bit more closely. Well, I guess not everything is in this column is a metal. Boron's not a metal, but when we start boron, silicon, arsenic, tellurium, iodine, astatine. Basically, when we start getting into that section of the periodic table, we start falling into these are all our nonmetals over here. And that little thing is what we call the staircase. So everything over here is pretty much nonmetals. Everything this way is metals. Now, these metals, you guys, that I'm going to put in, all right, we'll just use this blue. We'll use this pink color. Just so to be clear, everything that you're dealing with here in pink is also a metal, but you'll notice something, you guys. Most of these have more than one charge, okay? So they can form more than one type of ion. That's what these are. These are what we call the transition metals. And the transition metals are tricky, and you have to look closely at the transition metals because certain transition metals, like, say, for instance, iron, have two different versions of that ion. Some versions have a +2, some versions have a +3. Others, like zinc, only have one available ion, and that's +2. So that's going to become important as we figure out what type of ionic compound we're forming with these metals, okay? So everything in blue here, those are my nonmetals. Everything in yellow are what we're going to call simple metals. Simple in the fact that they only have essentially one ion available. And everything in pink, that's going to be our transition metals. And just remember, you guys, when we are dealing with transition metals, we have to watch out and see if those transition metals have more than one ion available to use in a formula. So with that said, the last thing that you're going to need is you're going to need this set of notes about naming covalent compounds. That's the last thing you're going to need. So there's a bunch of stuff that you need in order to successfully complete this page because you're being asked to do a lot of things. So let's take a look, you guys, at our first compound, which is right here. I'm going to zoom in a little bit so you can more easily see that. And we are dealing with NaO2. Yeah, NaO. So we have two different, essentially, chemicals in here. Sorry, you guys. I'm going to take a quick pause. So we have sodium and oxygen. One of the first things we have to do is determine whether our compound is ionic or covalent. We know the difference, you guys, because if we have a metal like this and a nonmetal, we know it's going to be an ionic compound. And we know this, you guys, because when we talk about stuff that you should know about chemical bonds, we have information that tells us the difference between one or the other, okay? So just know that we've been talking about this for a few days. If we are combining a metal and a nonmetal, like we are here, then it's going to be ionic. You're going to use, because we're dealing with sodium, sodium is a simple metal because it's in that first category. So as a result of that, we just use our simple name sodium oxide. And if you can't quite remember where to find that information, you want to look in this set of notes on the first page. Okay. Polar or nonpolar, it's neither. Remember, you guys, when it comes to polarity, polar implies sharing of electrons. And remember, you guys, in a covalent bond, we're not, or in an ionic bond, I should say, in an ionic bond, there's not sharing of electrons. The metal will give its electrons to the nonmetal. So there's no sharing, therefore there's no polarity one way or the other. So rather than saying polar or nonpolar, we just scratch a line through it. Okay? So now let's look at our next one. Our next one has two elements in it, carbon and oxygen. And if we look at our periodic table, we know that both carbon and oxygen are nonmetals. Okay? And we can go back here if you need to. Remember the ones I told you that were nonmetals. Carbon is a nonmetal.
Oxygen is a nonmetal, and as a result of that, we know this is going to be covalent. So if we need a reminder about how to name a covalent bond, we are going to use these notes right here that says naming covalent bonds. So we have carbon. Since we only have one carbon, we don't need to put a prefix in front of it. Now, because this oxygen is the second element in our compound, we do have to put a prefix in front of this because there's only one. So we're going to use, because there's only one of them, we're going to use the prefix mono. So this is going to be carbon monoxide. Now, because this is a covalent bond, we have to determine whether it's polar or nonpolar. And we're going to do that by using our periodic table of electronegativities. And that periodic table of electronegativities is right here. We can calculate that. We'll do that down here at the bottom. Actually, we'll just do it right here at the top. Oxygen has an electronegativity of 3.44. Carbon has an electronegativity of 2.55. If we do the math on that, we subtract 2.55 from 3.44, and we get 0.89. So this is our electronegativity range. So what we're going to do now is we're going to go back to this document that had our electronegativity ranges. 0.89 will fall in between 0.4 and 1.67, so we know that this is going to be a polar bond. We're going to say it's polar, and we're going to prove it by putting our electronegativity range right next to it. Okay, so far so good. Now I'm going to jump down to this one right here because this one is an ionic bond because we have a metal and a nonmetal. But this time, you guys, I have to remember that I'm dealing with a transition metal. And I'm just going to put that right here to remind myself. Which means when I'm naming this compound, I have to acknowledge the fact that I have a transition metal here. Now remember, if I look at my periodic table of ions, we need to see what different versions of iron I have. I have iron with a 2+, and I have iron with a 3+. Now remember, when I'm dealing with an ionic compound, my overall charge for my ionic compound has to be 0. So the first thing I have to do is I have to figure out what the charge of chlorine is. All right? So if I look here, I see that I have chlorine and a minus. That's another way of saying -1. So my chlorine has a charge, I'm just going to erase this real quick, of -1. But remember, you guys, I have a subscript down here. So I have to multiply the subscript by my charge, which means that I'm going to have a charge of these three chlorines overall of a -3. Now, I have to balance this out so the whole compound equals 0, which means that I have to have a 3+ right here, okay? So if I'm going to choose which version of iron to use, I'm going to use the version of iron that allows me to cancel out that -3 charge, which means I'm going to use iron F3. Now, I have to say that in my name. So it's going to be iron, and because I'm using the +3 version, I'm going to use a Roman numeral of 3 to signify that I'm using the +3 version instead of the... Oops, I got to let it focus here. Come on now. Focus, buddy. Anything? Is my autofocus not working? Let's tell it to autofocus. There we go. So I'm going to be using my +3 instead of my +2. That's what that Roman numeral 3 stands for. So it's going to be iron 3 and then chloride. It's an ionic bond, so I don't have to worry about polarity. Okay, good. Is that all I want to talk about? I think that's all I want. Oh, you know what? No, that's not all I want to talk about. The last thing I want to talk about is polyatomic ions. So let's drop down to, well, let's do this one right here. Now this one is a little bit tricky because you say to yourself, well, there's 3 elements in here. Here's calcium, here's carbon, and here's oxygen. Now that's usually a dead giveaway that you're dealing with something that's a little bit different. So as soon as you see that you've got 3 separate elements, you need to say to yourself, I'm probably dealing with a polyatomic ion. So if you can't remember your polyatomics, you can use this sheet right here. So you want to look and see what you have here. I have Ca, so this is going to be calcium. I have carbon and I have oxygen. So if I look through this, essentially what I'm looking for, I am looking for CO3. Because when we have a polyatomic, many times the polyatomics are the second thing in our compound. Sometimes they're the first, but not very often. So if I have a metal and then I have two nonmetals behind it, it's likely that I'm dealing with a polyatomic. I'm going to check my list to see if I can find it, and there it is right here. This CO3 is carbonate, and carbonate has an overall charge of 2 minus. Okay, so let's keep that in mind. So we know this is going to be an ionic compound because I'm dealing with a metal and I'm dealing with a nonmetal because this whole carbonate is a nonmetal compound. And now I have to name it. The good news is it's really easy to name any sort of formula with a polyatomic ion in it. So I'm going to name it calcium. Now the nice thing is that calcium is not a transition metal. Calcium is a regular simple metal. It's in column 2 and it has an overall charge of 2 plus. So this has an overall charge of 2 plus. Carbonate has an overall charge of 2 minus. So there really isn't anything big I have to do here. All I have to do is name it, and I'm going to name it calcium carbonate. So calcium for the metal that's in it, and carbonate because that's the name of this particular polyatomic ion. Again, it's an ionic compound, so I don't have to worry about polarity. Okay? So that's what we're going to do for this side. Now we're going to flip it over and work on the other side real quick because the other side is a little bit tricky. I'm going to start with this one right here. This is a covalent compound, so it's not that tricky. And it's just working backwards. I have carbon, and I have monoxide. So there's my prefix, monoxide meaning 1, oxide meaning oxygen. So I'm simply going to have that. That one's easy. The harder one is going to be something like this. Because with lead sulfide, what I have to figure out, I have to work backwards from this. I know that this lead, because I'm using lead 4, is going to have a charge of plus 4. So what I have to do is I have to look for sulfide. Here it is. And I see that sulfide has a minus 2. So right now, if I add up these charges, they don't add up to 0. So I have to get my sulfide right here to equal this charge, which means I'm going to need 2 sulfurs, which means now my overall charge is going to be minus 4. And now my overall charge on this compound is going to be 0. So if I have Pb4, it means its charge is 4. S2 is going to be my formula for this one. It's ionic, so I don't have to worry about doing polarity. But that's one of the things that you have to remember. When you're dealing with ionic compounds, only ionic compounds, don't worry about this for your covalent compounds. But if I have ionic compounds, it means their overall charge has to be 0, which means I have to make sure that I have the right subscript next to my elements in order to make sure that the whole thing is balanced out to 0. Okay. I am losing my voice, so that's all the talking I'm going to do for today. If you need help with this, let me know. Feel free again to work with the people at your table.